Okay, you might hear some talk in the background. There's a lab going on here, not for the course I'm talking about here, so this is not relevant to the lab. So even if you identify the people's voices, all you know is that they were in the lab. Okay, so I want to talk a little more rigorously about partial derivatives. In the preceding videos, I gave you the intuitive idea of this function drives a change in this variable, which then drives a change in this other function. Using one of the functions that we use, f of x equals the sine of x squared, we can write out the definition, at least the approximate value of the partial derivative. I'm not going to do limits. The limits are obvious, and you can read a limit definition of this thing anywhere. It's very much the same as this, but I want to keep it as intuitive as possible to eliminate what we did before. So what we have is f of x equals sine of x squared, so that I'll write it df dx, but that'd be your f prime of x, is approximately equal to f of x plus delta x minus f of x over delta x. In other words, the change in the value of the function, the change in y if you wish, is y equals divided by the change in x, which is the average rate of change of y equals f of x with respect to x. And of course, we have to understand rate of change. If we write out the expression for the sine of x squared, then f of x plus delta x is the sine of the quantity x plus delta x squared minus, and then that's minus f of x over delta x. Of course, x plus delta x squared is x squared plus 2x delta x plus the square of delta x, and then we have the rest of the expression for the approximate rate of change of f with respect to x, which is the approximate value of the derivative of f with respect to x. Delta x we understand to be small because, of course, this expression, to give you the actual derivative, we're going to take the limit of this expression as delta x approaches 0. So here we have the expression that just follows from this definition for this function. Okay, well, if delta x is small, then delta x squared is as much smaller than delta x as delta x is smaller than 1, let's say. In other words, if delta x is small enough, delta x squared is negligible. And that's for small delta x. Okay. So now what we have is a sine of x squared plus 2x delta x. Well, the sine of any quantity plus a small change is approximately equal to the derivative of the sine, which is the cosine, times that change. Okay, so this would be then by local linearity, the sine of x squared plus 2x delta x is approximately equal to times this. If delta x is small enough, 2x delta x can be really tiny. So we just use local linearity to get this. I might talk a little bit more about local linearity. And really this isn't a good proof because at this point, I'm sort of using some concepts in a circular manner. That can be gotten around, but we're keeping this sort of intuitive, so we're not totally rigorous by saying this. So this equals what? Well, f of x, and I probably should have written it out that way, both here and here. F of x is just the sine of x squared. So now we have a sine of x squared minus a sine of x squared. Well, that just leaves us a cosine of x squared up here. So we have 2x times the cosine of x squared times delta x divided by delta x. Well, that's 2x times the cosine of x squared, which is, of course, f prime of g of x, f prime being the derivative of the sine, which is the cosine, g of x being x squared. Times your g prime of x, which is your 2x, because g of x is your x squared. Okay? Now, in terms that I used previously, we see that by squaring x, the small change in delta x drives a change of 2x delta x in the argument of the sine. So that we're driving the argument of the sine by a factor equal to the derivative of x squared. Of course, the reason the derivative of x squared is 2x is because of this expansion, the binomial expansion. So again, we're kind of a little circular, but we still get the idea. So the big deal is, since this is x squared, when we square x plus delta x, we get the 2x delta x, which is what gives us the 2x down here. This is the rate of change of g of x. And we multiply that then by the derivative of the sine function evaluated at x squared. So there it is. And the driving term, the delta x here gives you this, gives you this. Okay. This could be made much more rigorous. You can look at a rigorous proof or ask me to do one.